In lesson 6.5, we're going to deal with exponential and logarithmic equations, sort of pulling together all that we've done so far. So let's get started. Pause to look at the objectives, keeping in mind that you could click on this watch as well, and the authors will provide a oral narrative of what's going on. And what we'll do is take a look at the first part of this video here.
Hello and welcome to this video on exponential and logarithmic equations. We have 3 lesson goals to consider. In the first one, we'll look at solving exponential equations. We'll then learn how to solve logarithmic equations, and finally, we'll take a look at further applications of exponential and logarithmic equations. So let's get started. The equations x equals a to the y and y equals the log base a of x are equivalent. The functions f of x equals a to the x and f inverse of x equals the log base a of x are inverses. The log base a of a to the x is equal to x, and a to the power of the log base a of x is equal to x. In particular, the log base a of 1 is 0, since a to the 0 is 1, and the log base a of a is 1, since a to the first power is a. The log base a of x times y is equal to the log base a of x plus the log base a of y. The log base a of x over y can be written as the log base a of x minus the log base a of y. And finally, the log base a of x to the r is equal to r times the log base a of x.
So as you see, it's a rather good review of what we've been doing so far. And then going back to the text of Learn, again, you can pause, read this, scroll up a little bit, and there is a listing again of the logarithmic properties. Now, what we're going to do is some examples using these properties. Now, when we do the examples, you'll note that they're going to show you the sequence in detail, but if you know the overall sequence, you can kind of do some shortcuts, and we'll mention that as we go along. Now, in example 1, we're going to take a look at this, which is in exponential form. And actually, there's more than one way to solve it. So let's follow what the book is showing. Take some notes as you do this, step by step. I'll get my pen working here. So there is the initial equation. Notice this is in exponential form. Now, if you take the natural log of both sides, that's what they're doing here, natural log of this side, natural log of this side. When you do that, you can take your exponential portion and move it out in front. That's one of the rules that we've said. Now, how would you solve for this? Well, you would divide both sides by this, which is what they're doing. Now, again, you want to solve for x. So we're going to take this 2, transpose it to the other side as a negative 2, and then you have this. Now, how would you solve for a positive x here? Well, you're going to divide both sides now by a negative 5. So all of this then divided by a negative 5, and over here notice a negative 2 divided by a negative 5 gave you a positive 2/5. And they're showing this negative 5 as you divide this, just putting it in the denominator and making this whole term a negative. So again, this would be the exact answer. And putting that into a calculator carefully will give you an approximation. Now, another method to do this is just to go from its exponential form into an equivalent log form, where we say the base 3, log base 3 of 11 is equal to the exponent. And from there, it pretty much is the same protocol. And notice you get the same answers. One was in the natural log, and this one is in regular log. And you could write it in natural log as well. And here you could see they're using what is called the change of base formula, where you could have gone log of 11 divided by log of 3. Instead of using logs, they've chose natural logs. This would be the common log. Again, the answers are the same. In example 2, as we see, a base to the exponent, a base to an exponent, it's rather tedious as to the protocol for solving it. So I'm going to let you view the video that is offered by the authors.
Hello. In this example, we'll be solving an exponential equation. Solve the equation 5 to the 3x minus 1 equals 2 to the x plus 3. Express the answer exactly and as a decimal approximation. When we're solving exponential equations, one thing you should look for is to see if the bases of the exponential terms are the same or could be rewritten as same base. So for example, if the 5 on the left-hand side was a 4, we know that we could rewrite 4 as 2 squared. And then we could use some properties of exponents to simplify this and make our lives a lot easier. Unfortunately, in this case, we can't do that. Our bases are 5 and 2. Those are different. And we can't rewrite 5 as a power of 2, and we can't rewrite 2 as a power of 5. So it seems like we're going to have to go straightforward here with some evaluating logs and using log laws. Let's go ahead and take a logarithm on both sides. When you do this, we are going to be using the log law that lets us bring the exponent down front, but you can use log of any base that you want. You can do the natural log of both sides if you like. You could do log base 5 or log base 2, or you could just use the common log. Whichever base you use for your logarithm, you're going to get the answer that is equivalent. It just might look a little different. For this example, I'm going to use the common log, which is log base 10. I'm going to take log base 10 of both sides of this equation. Now, the reason why we do this is so that we can use that log law that will bring the exponents out front. Ultimately, our goal to solve this equation is to get x by itself, but the x's that we have in our equation are up in exponents, and our only hope to bring them down is by using that log law. So by the log law, 3x minus 1 will come out front, and it will be multiplied by log base 10 of 5. On the right-hand side, the x plus 3 will come down, and will be multiplied by log base 2. Now that we've done this, we have rewritten our exponential equation that was difficult to solve as an equation that we've been solving for a long time. This is just a basic equation with the power on x being 1. The only difference here is that a number that we're using involves logarithms. When you write log 5, that seems really intimidating, and there's so much letters involved. But remember, log 5 is just a number. And the same thing goes for log 2. So whenever you start solving this equation, just keep that in mind. Log 5 and log 2 are just numbers. So since they are just numbers, we can still do things like distributive property. We can still do things like adding and subtracting on both sides. We can still divide both sides by numbers. All of our favorite algebra solving techniques are still okay. Just have to keep in mind that these are numbers. Let's distribute that log 5. We'll have 3 times log 5 times x minus the log of 5. And on the right-hand side, we'll have the log of 2 times x plus 3 times the log of 2. Let's get all of the x terms on one side and all of the non-x terms on the other side. Let's see. I'm going to subtract log 2 times x on both sides. And then I'm going to add log of 5 on both sides. Now, we would like to get x by itself, and when you look at the left-hand side, you can see that we have 2 terms, but both of them involve x. So let's go ahead and factor that x out of those 2 terms. And what we're left with is 3 times the log of 5 minus the log of 2, and all of that is equal to 3 log 2 plus log 5. Now we have our equation as x times some number, although it's really scary looking, equals another number. We know we can get x by itself by dividing both sides by that number. So we'll have 3 times log 2 plus log 5, all divided by 3 times log 5 minus log 2. This is an exact answer for this equation. And if you put all of this in your calculator, you can get a decimal approximation, which will be 0.892. If you would like to simplify this a little bit, you can. We can use some log laws to clean this up if you'd like an equivalent way to give an exact answer. And it's also just really good practice for your log laws. Let's see. Let's come over here to the side and do exactly that. 3 times log 2 is the same thing as log of 2 cubed. And 3 times log 5 is the same thing as log of 5 cubed. See, 2 cubed is 8. So in the numerator we have the log of 8 plus the log of 5. Well, that's the same thing as the log of 8 times 5. In the denominator we have, 5 cubed is 125. We have log of 125 minus log of 2. According to log laws, that would be the log of 125 over 2. So you could rewrite this as the log of 40 over the log of 125 over 2. This is an equivalent exact answer for this logarithmic equation.
The water's coming inside.
So looking at this example again, we see the key is converting it to its logarithmic form. And let's just go through this in some detail. See if we get it all loaded there. Okay. And then going through the steps. You want to be sure you know what the steps are. So there's our original equation where we have a base, exponent, and exponent. But since the bases are not the same, we can't use that older technique of having the exponents equal each other. But we can convert it to logs. The interesting part of logs is now we can take our exponent and put it out in front. Now we're going to multiply each of these by distribution and get this. We're going to put those with the x terms all on one side using algebra. And there we're just transposing this to this side and this to this side. Notice the sign change. Now we're going to factor out the x and now divide both sides by this, and simplifying, putting this right into your calculator. You want to see that you'll get an answer like this. So in your practice that we'll do shortly, this is the protocol we would follow. And if you have notes on it, you're just reviewing and using that model to substitute new values. Going on now to example 3. We see this expression. It's in log form. So take a moment and we'll scroll down and take a look at the solution. And again, I could write it out, but it's written out nicely here. So there's our original equation in log form. So remember, we can convert log form to its exponential form. Base to an exponent equals the answer. So our base is 7. Our exponent is 2. And our answer is 3x minus 2, which is what they have here. So this side becomes 49. We're going to transpose that negative 2 over where we would just add 2 there. And that's what they've done. They got a total of 51. Divide both sides by 3 now. And they get x equals 17. Again, this is one of the easier ones we're going to be doing. As we do example 4, notice it's in log expanded form. So we're going to put it in log condensed form and then convert it to its exponential form and solve for an answer. Before we go down, though, it's important that when we get solutions, we have to check that the value we have for the answer is appropriate for our original example. And the key is you cannot have a negative log value. All right, so let's take a look at this. They have it all worked out nicely here. Let's check it out step by step. So there's our original expression here, equation. We're going to convert it to its condensed form. So this side stays the same. Here, since this is subtraction, we're going to divide by this. Our bases are the same. So our exponents then, or our answers, equal each other. So this is what we have. So to go and solve for x, and we have x over here, we're going to multiply both sides by 2x minus 3. Now here they cancel out. We've gotten rid of fractions. We're going to distribute here. which is what they show. We're going to then take all of our terms from the right side, bring them over to the left side, so we have a quadratic equation in standard form. And generally these will factor, and you take each of the factors and equal it to 0 using the zero factor property that we spoke of a long time ago. So we get as our roots, x is a negative 1/2 and x is a 3. Now we're going to check those in our original. I'll move it up so you can see it. When we put the negative value into our original, we see you can't have a negative log. So we have to reject this as a possible solution. When we put the 3 in there, it works out very well. So our correct answer then is x equals 3. If you were to put both values into the answer box in the software, they would count it incorrect. So again, you have to check these to see if the solutions you get meet the qualification of logs. You can't have a negative log. In example 5 now, we're going to look at applications. And this specific example is on compound interest. So take a moment to read it, pause, and you remember our compound interest formula. Now this isn't continuous interest, this is compound interest. And for a quick review, this is compound interest formula, the one they're using here, and this is continuous compound interest, which is this one. Now we did one like this earlier, and now we're going to substitute into here, and you see this is what they've done. It's compounded quarterly, so our n value is 12, and it's 12 times t. We don't know how many years it would take to get to this. So some background. Now let's look at the actual work to solve it, in which we use our knowledge of logs and exponents. Now you want to write down the steps of this item by item so you know what's going on. And if you get an example like this, this is what you'll use as a strategy. So there's our original substitution. The first thing we're going to do is divide both sides by this. On this side, it's eliminated. On this side, you get this. Now, they're keeping all these zeros. I would just do this simple division here, make it a little easier, but if you're using your calculator, you could leave it this way. Now, you're going to take the natural log of this side and the natural log of this side. Now, the natural log of e to the e power just becomes then the exponent part here. And let's look at that more closely. And what they've done is they've taken 0.048 divided by 12, add a 1 to it, and then they got this value here, and they took that, moved it in front, and that's where you get the 12t natural log of this. Okay, so how do you find the answer? Well, you're going to divide, because you want to solve for t. So you're going to divide both sides by 12, natural log of 1.004, which is what they have right there. This divided by this, and the beauty of the calculator is you put that into the calculator and you get this. Now, what does that mean? Well, that means 1.82 years, which if you convert it to 1 year and then months, it's a little less than 10 months here. It will grow from this to this, and you've used logs to find the answer. Now, the proof of the pudding, so to speak, of all of this is later you're able to do the practice and then the certify and have the protocol to do well on your tests. So for example 6, and there's only 2 slides left, what is it that they're asking? Well, they're dealing with radioactive carbon dating. So take a moment to read this over. And I might add from my biology days, carbon-14, as you live, any living organism takes in carbon dioxide. So there's an equilibrium in the living organism with the environment. But once the living organism dies, that exchange doesn't go on, and there's a reduction in the amount of carbon-14, which is radioactive, in the remains of the organism. And then by measuring that and comparing to what would be there today, we can find out how many years it took to do this. And we say there is a half-life. That is, if you had 1 unit of something, what time would it take to get half of that, which would be half of a unit, and so on. So here is the general formula, and then we want to figure half-life. So A sub O is going to be 1, and this will be 0.5. So let's work on seeing this in action here. And instead of 0.5, they're dividing it by 2, 1/2. 1/2 is 0.5. You could use either 1/2 or 0.5 here. And you're going to convert it to its natural log form. So the natural log then of 0.5 is equal to, and this is where you can use a shortcut. They're showing you the actual steps here, but it will be natural log of 0.5, which is 1/2, divided by this portion, which is a negative 0.000121, will equal t. And that's what they have down here. Now they're showing you the logarithmic conversion. Remember, by having natural log, the exponent goes from there out in front, and this configuration, natural log, base e of e, just becomes a 1. So it gives you this step. Then you divide both sides by this, which is what we're showing here, and you get t is this. So this is the half-life. That would be for letter A. Now for letter B, we're going to plug in our knowledge, or data. We're starting off with this much. This is current. And we find that it had this much. So we're measuring now what is the age of this antique organism, in a sense, that started off with this but now has this. Using the same protocol, we're going to divide both sides by this, get this, convert this to its natural log form, And keep in mind that the natural log of this just becomes the exponent. We divide both sides by this portion, and we solve for t, and we get approximately 3,533 years. So that's a dead thing here, and we've measured its estimated age using radioactive carbon dating. Now, for the last slide, there's basically background information, analysis of a stock market investment, and they're kind of going through it. You can pause and read it if you like. They're showing you what's happening. Now, I haven't done the practice for this, and I'm not sure they're going to give us an example like this for practice. I think it's primarily what we've done. If we need more information on this, I will include it on our classwork practice lesson that I'll be working on later today. All right, this will wind this one up.